Chris Redino. I have my PhD in theoretical physics, where I learned how to use my mathematical, statistical, and programming skills to solve problems, but those are problems no one wants to pay you for, so now I'm doing data science using the same kind of skills for hopefully something that's still fun. And the data here comes from the New York City, Health and Mental Hygiene Department, their annual survey. So what they do is they ask all kinds of different health questions from about 8,000 New Yorkers in all the boroughs. What's interesting about it is that it's regional. So they don't use zip codes, they use these predefined neighborhoods. So when you see UHF in the data I'll show you later, it's referring to these areas. Okay? So the name of my project, if I scroll back up, called it Health Indicators and Geographic Factors. So in particular, the one I'll focus on is the obesity rate. Okay, this is just one of the things the survey looks at, but it also has things like diabetes and venereal disease and all kinds of different health indicators. Okay, and what's interesting is that it does it geographically. It does it by neighborhood. Okay, so I explored this a little bit in this app. Okay, so if we go to the map, let's just focus on the top one at first. I'll explain what the bottom one is later. Okay. So you see it's broken down by zip code, okay? But then the colors tend to be in larger chunks, and those chunks correspond to those United Health Fund regions that I showed on the other map. And what you're seeing is the darker the color, the larger the obesity rate, okay? And before we dig into this data anymore, I think one thing that jumps out right away is how different it is just by looking at neighborhood, how likely it is you'll be obese, okay? So there's a key here, all right? But just off the top of my head, the skinniest parts of Manhattan, only about 5% of people are obese. Obese being defined as a BMI, that body mass index of 30 or more. Okay, that would be considered obese. So only 5% of people are obese in lower Manhattan, whereas parts of the Bronx and parts of Brooklyn, it's as much as 40 or close to 50% of people are obese. So just the neighborhood you live in has a huge effect. Okay, and this jumps out at me. So this tells me, it's not just genetic. There's some lifestyle thing going on. It doesn't mean it's necessarily a lifestyle choice, okay? But where you live, there is some connection, okay? Now, I'm not going to do any sort of rigorous statistical analysis, but we can do two things here, okay? One thing we can do with the data, besides just show it like this, we have this box that's a sample here, and we can take different slices of the original data, and we can see how it shifts, okay? So you can just kind of play with this. One thing we can see if we check off males, okay, it'll take a minute to refresh. Okay, you notice some parts get darker, some parts get lighter. It shifts a little. But what's interesting is you could click a bunch of these, and you will see small variations over different populations. But the geographic factors are still important. It's still Manhattan that's skinny. It's still lower Brooklyn that's more obese. So I think this is interesting. It shows that something's happening here. We want to try and understand this. And more than anything, this app is just meant to explore that, not really answer that question. Okay. Yeah, you can look at different age groups. You can look at different ethnic groups. Okay. And then what I also have done, okay, the bottom graph, scrolling poorly, but you see these predictors. Okay. Now, what I've done here is I've made a not so rigorous model. Okay. When I say not rigorous, it's because I didn't validate this with any of the diagnostics that Brett talked about. But all I've done is the point of this exercise isn't to build an accurate model, it's to explore choices of models, okay? So what we're doing is, I used a different data set, okay? In addition to this health survey, I took the New York State health inspections of all the restaurants in Manhattan, okay? Which have their zip codes, and I have zip codes here. So I could actually stick these data sets together, and what I could look at is, I could look at the counts of different types of food vendors and see how this actually affects the health. Okay, so the way I've done this is, I have some funny categories here like fast food. So if I unticked everything else and just looked at fast food, what I would be doing is I'd be making not so rigorous prediction of how the count of fast food restaurants in your area reflects how likely you are to be obese. Okay, and I say not so rigorous because again I didn't do the diagnostics. It's just a simple fit. Okay, and we could do a fit to a whole bunch of these guys, and you could play with this also. Okay, so the scrolling is not great. I have to find Manhattan again. There it is. Okay. So for example, we could take fast food out of the picture. Okay? And it tends to do the best, I think, when you include all these factors. I think that tells you something maybe a little bit wrong with the model in the first place. I mean, you could play with this on your own, but you might think, vegetarian food is going to have a different effect than fast food, for example. Okay, but what I saw, and when you might see too if you play with this, is when you count all the restaurants, it tends to have the best fit. So how good a fit does it have without being numerical, without being rigorous? All we're doing here is comparing how the top picture and the bottom picture look like. Okay, so it looks like what counting restaurants does. It gets the main features right. Okay, Brooklyn, the Bronx, they're a little bit darker. Okay? Manhattan, it's a little bit skinnier. Out near Flushing, it's a little bit skinnier. Okay, so it gets the main features right, but it's not enough to explain the whole story. Okay, you still see like the darkest regions. Okay, they're not matching up correctly. So what I've done here is I've done a multiple linear regression using just the counts of the different types of food vendors. So for example, this colored chunk is one of those UHF regions, one of those United Health Fund regions. Okay, so what I'm doing is I'm counting how many fast food places, how many pizza places, etc. And I do this for all the regions. Okay, so there's 42 regions, 42 points, and I have counts in all those 42 regions, and then I just fit a line to it. Okay, so it's really simple. Okay, it doesn't mean the actual relationship is linear, and we haven't gone ahead and checked that. Okay, and one thing you might want to worry about, especially when you're doing this model selection, is these might not all be linearly independent. Okay, there could be a lot of collinearity here, and that might not even be inherent to the problem. That could be inherent to the New York State Health Inspection, because a lot of times these are labeled pretty badly. Okay, so part of the cleaning of the data was me actually manually fixing some of them, because a lot of them are labeled inconsistently. I don't know if the New York State Health Inspector or the restaurant themselves reports their category, but for McDonald's at least, some of them list themselves as burgers, some of them list themselves as American food. In fact, American food is just the default, so I just went through and all the fast food chains, I relabeled them as fast food. But because the labeling is not perfect, that's one reason at least. You might think there's a lot of collinearity, so then you want to be careful about this. And I think that collinearity also, that might be why I get the best fit when I just kind of throw all these things together in this kind of sloppy way. But you can still see, if this was complete nonsense, I think you wouldn't see anything at all. But if you want to do something serious, you have to look a little closer. And there are academic papers that look at this, and I think there's a little bit of disagreement on what's actually happening. Some people think it is the availability of quality food. Other people think it's has more to do with just economics. Like, for example, last week I was eating my breakfast in Brooklyn. I was having lunch up here. So obviously you don't have to eat where you live. But whereas you do have to be able to afford where you live. So maybe economic factors are more important. But there is correlation. Okay? So in more than one way, there's collinearity here. So it's a messy problem. This just lets you explore it, but lets you do it in a few ways. You could look at the different indicators, and sometimes you see some interesting things. Like, I won't do it because I don't want to refresh this a dozen times, but if you play with this on your own and you only eat vegetarian food, what you'll find is, because most of the vegetarian places are a little more expensive because they happen to be located in Manhattan, the fit gets really good in Manhattan, but it gets worse everywhere else, meaning these color scales are actually the same. If you only fit the vegetarian, the colors between Manhattan will match pretty well here, but everything else will be a little worse, if that makes sense. And it's not just the maps. You could also look at the raw data. So again, you have UHF, United Health Fund zones. Okay, and each zone contains multiple zip codes. So like, for example, you see 104 repeated a bunch of times. That's because 104 contains each of these zip codes. Okay? And then you have the actual measured rate. Like I said, in the raw data, it varies between like 5% obese rate and as much as almost 50% obese, which is huge when you think about it. And then there's the predicted rate from the model. So if you play with these tick boxes, you'll see the rates do change. And then if you play with the other tick boxes, you can take off columns, and then the fit will change. And then also, when you're just looking at the data, you just get one number. But really, it's not just the rate that's obese. You want to know, are these people grossly obese? Or are they just barely over the line of 30? Okay. So we can also look at distributions of BMI. Okay. So this is the total distribution of BMI for everyone in Manhattan. Okay. And you see the bins overlap a little bit. So this aqua or whatever, what color would you call that? Cyan. That's obese, and the salmon is not obese. Okay. And it's overlapping a little because it's at 30, and this bin spans 30 and a little less. So that's what's happening there. Okay, and this is just raw count. This isn't normalized at all. So there's 8,000 people in the survey. Okay, and that's how it falls out, or a little more than 8,000. Okay. Could also break down the distributions by those neighborhoods and see how they shift, because we know different neighborhoods should be heavier than others. Okay. And again, this is in counts, so now the counts are much smaller because we're breaking up the population. Okay. And the scales are different because they're trying to fit all these guys on the same scale. Okay, so you see some, they have more salmon, and others, what's a good example? Others have more cyan. Okay, so we have heavier and lighter communities. Okay? And if you change the populations, by taking these guys, you can see how all these shift.
Do you just ethnic position?
You want to see what ethnic?
Just
ethnic and position. So I mean, all I have to display is either the map, the raw data, or the distributions. But if you want to look at the effect of ethnicity, I could take one ethnicity at a time or one group of ethnicities. So if you want to see, for example, yeah, let's look at just black and Hispanic people. So we'll take out whites, Asians, and their catch-all, because I guess that's the level of accuracy for the survey. So we'll refresh in a second. And we'll see some neighborhoods do get a little heavier. And we'll also see they'll rescale. If this will load in a second. Might be faster on your machine. There we go. Okay. And you see some of these, some of the neighborhoods, they lost all their counts. If that makes sense. Okay, but maybe some of these neighborhoods were predominantly white or Asian. Okay. And we'll see some of them, they look more blue now, because now we're only considering that subpopulation. Okay. And also, it's maybe more interesting, you could go back and look at the map now. Okay? And look, both maps get a lot more dark. Okay? Now, we still have those same, well, for the most part. Maybe I didn't actually look at this particular combination. This is real interesting. This was white before. Okay? So ignoring this part, which is interesting, we still mostly see the same pattern. Okay? And the prediction, again, it's okay, but it does miss some features. Okay? But also, this is a little hard to interpret because we don't have the same statistics in each region. Maybe we only have like 2 Latino guys living here, okay? And we don't know that. I mean, you could extract it from looking at the distribution and then looking at this, but not in the quickest way. If you wanted to look at that, there's probably an easier way to visualize that data, okay? And yeah, so you could play with this, but one last thing I want to mention. You might say counting restaurants is kind of silly because these regions are different sizes, okay? So, for example, this UHF in Brooklyn is like that big, okay? Whereas this UHF in Lower Manhattan is that big. So should 5 McDonald's here count the same as 5 McDonald's here? That seems kind of silly. So you can see, if you want, okay, there's this predictor scaling. Okay, right now it's none, which means we're just fitting our model by just counts of restaurants. We can also do it by number of restaurants per unit area, okay, per square mile. Okay. And I can't guarantee it'll look better for this subset since we're only looking at some races, but we can see the effect. Okay? And I think it does, in general, improve it. Okay? So all I changed was the fit, so it should do it eventually. I know I have to refresh it so many times. But this one shouldn't change because all we changed was our fit. Okay? We changed how we scale by area, so this one should change.
But you cannot just run prediction on ethnicity versus obesity.
So I'm running. So the measured variable here is the obesity rate, okay, and the predictor variable is the restaurants. When I change the rate, the population, okay, all I'm changing is my.
You cannot eliminate restaurants.
Yeah, these change the sample. I could. You're saying you want to take race and you want to put it down here in the predictors. Yeah. I mean, you can't look at that directly on the model, but again, the model is mostly there for visualization purposes, not there for prediction purposes. So if you want to see the effect, you do get that, and that's what we're looking for. We're not looking for an output of numbers. We're looking out for we're looking for an output of visualization. So if we want to look at the effect at race, we don't see how much better it fits. We look at how the colors shift. Okay. So we're trying to visualize a lot of effects at once, okay? Instead of having a whole bunch of different models. That's the idea. Okay. So I think that's most of it. Oh, I guess I could bug you with one last thing. You'll notice here, this isn't perfect. There's some gray dots. some gray regions. Do you guys have any idea why? Remember, these are zip codes. Why would some be no data? That's a good answer. Any other answers? His answer was it was an office space. College? College have residents. Okay, so it's a trick question, okay, because there are multiple answers. There's multiple reasons why zip codes won't work. Office space is a good one, okay? This is Penn Station, and it's actually, that zip code is in Z coordinates under Madison Square Garden, so they have no residents. So that's right for this point. Different points have different reasons. Here's LaGuardia, okay, that has no residents. Okay? And some of these, the survey, I used the most recent one I can find data on was 2013. The zip code data I used to generate this map is current. It's hard to find archived zip code data. When populations grow in trendy neighborhoods, like, okay, so where's Williamsburg? Williamsburg, okay? Gets real popular, a bunch of people move in, they add a zip code, okay? So the zip code didn't exist in 2013. Okay? So zip code, that was the messy part. The shiny was not that bad, merging the data wasn't that bad. Making the zip codes work and understand why they don't work, a lot of it's case-by-case basis. Why is this happening? Maybe there's no population, maybe it didn't used to exist, maybe it's outside the survey region, there's all kinds of reasons. Okay, so I think that's all the rambling I'll do. If there are questions, I'd be happy to answer them. No? Okay. One question? Sure.
Since you have a predictor, is there kind of time series can you do to predict the future?
So, yeah, so looks like there's some relationship. We can't say there's correlation until we have a series model, but you could do time series data because, for one thing, the survey data, it does happen annually, okay? And the geographic data and the food data, that also happens annually. Your restaurant has to keep being renewed for the health inspection, which is how I got these counts. So I can look at that over time. The difficulty is twofold. For the inspection data, they might change the category year to year because they're bad at reporting it, they're inconsistent. So I can do my own thing where I make my own categories, but it takes time, and a lot of it's manual. I have to look at a bunch of restaurants and say, is this category right? And that's manual, it's not automated. And for the health survey, it's kind of the same thing, it's inconsistency. So year to year, they might change the zone a little bit, or they might rephrase the question a little bit, so, or the sample size might not be as representative of all ethnic groups, things like this. So I think you could do it, but it will take a lot more massaging of the data to make it a time series. But then you can see, like, okay, the heavy population moved over here. Did the McDonald's follow them or vice versa? You could see something like this, okay? Yes?
Are people self-reporting their
Yes,
obesity?
they're self-reporting heights and weights. Okay, so there's, yeah, it's all survey data, so it's, there's that asterisk on all of this, yeah. And yeah, it's also, been brought up when I showed this before to my classmates, that BMI is not necessarily the best way to show obesity because, it's two parameters to fit the whole range of human body shapes. So I think those are both fair points. So this is the best we can do with publicly available health data is hard because, patient confidentiality. So surveys is usually how you're going to get it. So it's usually going to be volunteered. And if it's volunteered, it also means it has to be in simple terms, like a two-parameter thing like BMI.